Okay, so we will start the class. I hope you can see the screen and
Yes, sir. I can see the screen.
okay, okay. Yeah. So I'll give a brief introduction to myself. So my name is Syed Shabir Ahmed. So I'm a PMRF scholar from IIT Madras. So I work in the area of digital twin finite element model updating vibrations related to these things. And as everyone knows that this course is taught by Professor K. Ramesh, and he is also a professor in my department, which is Applied Mechanical and Biomedical Engineering department in IIT Madras. So if anyone has any questions related to uh, the course, you can ask it here in the session. And also, we have a discussion forum through which you can ask your question. Like you can send a message on the discussion forum. There are other TAs related to the course who will be able to help you. So this session is aimed at aim to help you solve the assignment problems, weekly assignment problems which are given. So last week, uh, last week there were three lectures. One was primarily focused on straight. So in that there is one lecture I think based on stress strain relationship. One second. Hello. Okay. So what your exam is going on from week 6? Just trying to- Devashish, just give me
Yes,
a.
sir.
Devashish, yeah, what were you saying?
No, sir. I only see the week one fast video, and remaining two videos are pending. My exam is going on, so I'm not attend the remaining two videos. So that's I
Okay,
attend.
okay, okay. Okay, okay. Okay, I'll give you a brief recap about what happened in those two videos.
Sure, sir. Thank you, sir.
So, the first video was on stress strain relations. You might have watched that.
Yes, sir. I already was.
Uh, and the second relation was interrelations between various elastic constants, relationships between elastic constants. So, like we have different elastic constants, like Young's modulus and Poisson's ratio, and we have the bulk modulus and also the rigidity modulus, shear modulus. So these four uh, elastic constants are there. Like Young's modulus relates stress and strain, and Poisson's ratio gives you uh, the relationship between lateral strain and longitudinal strain, and bulk modulus is basically uh, we have volumetric uh, whenever a load is applied in three-dimensional body um expands or is compressed. So that property is given by the bulk modulus, and we have the shear modulus, which between the shear strain and shear stress. So, and the third lecture was on thermal stresses and thermal strain and thermal stresses, like how it is done. Thermal strain. These are basically three videos, which three classes which happened. Okay, so we'll see some problems. I'll also explain you what you have missed if you have not if you have not attended the class. Let me know, like if you have any doubt. I'll give a brief. Okay. Yeah. So first question is, we have a graph like this, stress strain graph. This is a stress strain curve. So this gives the stress. Stress is always on the y-axis in megapascal, and we have the strain. And what is the behavior of the material from the stress strain curve? So what can be if you know like because you have watched the lecture, if you know, you can tell me the answer or I'll tell you. So basically you can see there is a stress from, this is from 0, and it is linearly increasing up to this point, and after that you can see that strain is increasing, but the stress is remaining constant.
The
So
elastic perfect plastic, sir, this one.
yeah, yeah, elastic and perfectly plastic. Elastic, perfectly plastic. So because this is a horizontal line, that's why we call it as a perfectly plastic uh, material, elastic and perfectly plastic. Suppose if you have like this, something like this, then you call this as strain hardening, uh, because the slope is decreasing, and for a little bit increase in stress, there is lot of strain. So this is like this, and there are lot of other curves like you have bilinear elastic plastic like that. And the other thing, there are interrelationships which were discussed in the second lecture. So the relationship between E and G is the shear modulus can be given as G is equals to E by 2 into 1 plus E. So basically we have if we have E and mu, E and mu, that is the Young's modulus and the Poisson's ratio, you can get the shear modulus by using this relationship. So in this E and mu, there are only two uh, independent elastic constants. So because if you know two, you can get the other one. So that's why we say for an isotropic material, there are two elastic constants. So if we know two, we can get the other one. So that's why this relationship has been derived in the class. Uh, it's like a simple, very simple derivation. Like you can use it, you can do it using the principal strain approach, principal stress and principal strain. Sorry, the Moore circle approach for 2D 2D case, and other case also was discussed for 3D three-dimensional. Other kind of derivation was also discussed, but we'll just stick to the formula because you don't need to remember that. You if you watch the lecture, you will just get just like you don't need to remember the derivation as of such, but just watch the lecture when you have time after that, so that you get the sense of how it is, how this relationship is developed. And also, we have the relationship between E and K. So, bulk modulus and Young's modulus, that can be given as K is equals to E by 3 into 1 minus 2. So, here also, if we know 2, we can get the other one. So, bulk modulus can be uh, uh, derived by this. So, bulk modulus is basically, so volumetric stress means like if your body is there three-dimensional case, uh, some uniform stress is applied in all the three directions like sigma, and there is volumetric strain. Volumetric strain is delta V by the capital V. So change in volume by uh, original volume. K is equals to sigma by E epsilon V. So volumetric strain can be given as that. So this volumetric strain also can be given like this epsilon xx plus epsilon yy plus epsilon z. So this also has been derived in the class. That is also a very simple derivation. You can just watch. and get a sense of how it is derived. But you just remember that some of the three axial strains will give you the volumetric strain, and this is the case. So, and the relationship between if you have uh, relationship between Young's modulus, bulk modulus, and the shear modulus can be given like this: E is equals to 9 kg by G plus 3k. So this is nothing but from this, either from this or this equation, you just take, let's say, you just get the value of mu from this equation by rearranging the things. Mu is equals to, you get something, and you substitute in this, you will get this equation. So we are just removing mu from the equation to get the relationship between E, K, and G. So 9 kg by G plus 3k. So these three formulae are important for you whenever you go for any competitive exam, because sometimes they expect you to remember this. Like uh, if you are planning to uh, give gate exam, or let some other state board, state or central government job exams or POSB examinations, these relationships will be useful. So derivation is not that important to remember, but we have to get the sense like how it is derived. So these three relationships are very useful to get an idea of how two elastic constants are enough for an isotropic material, and using those two, we can get the other one. The next question we will see. We have a tension test conducted on a, yeah, Devashish.
Uh, Sir, the specimen which is tested, we got
Ah,
the for the mild steel that the failure happened at nearly 210 or 235 gigapascal.
hmm.
So what is the specimen diameter, sir? Because it is very according to the area vary. So the strain and load is also vary. So, but in the standard, the stress strain curve, we always plot a graph. So
Yeah, yeah.
what is the diameter of
Uh,
actual?
so there are ASTM standards are there. Uh, I think 50 mm. In last class we discussed 50 mm, and 50 mm is the gauge length. You have a dog bone sample, and diameter is something. I forgot the diameter. But the thing is, whatever the specimen you take, the graph will be similar. Like you will get the same kind of graph. This graph, you will have the upper limit, upper yield point, lower yield point, and strain hardening and strain softening, and then the failure. So the just this graph will be same for any specimen you take. Like diameter, you can increase, decrease; gauge length, you can increase, decrease. Because this is tension test, this will remain same. So the graph will be remaining same, but but when you go to compression, things are different, because if you take a long rod compression test, uh, we don't study it here, but I'm just saying, if you take a long rod and you apply a compressive load, it may buckle because of eccentricity or some other factors. So actually, you are not doing a, compression, but it bends and breaks before it reaches its compressive strength. So for tension test, I don't think there are as such hindrances while conducting it. But you have to make sure there is gauge length that you can measure, and the cross section is uniform. The gauge cross section is uniform throughout.
Understand, sir.
Yeah,
So that means
that
the
is like.
graph.
Hmm.
That means the graph is remaining same, but if I change the specimen dimension, the magnitude only change the strain magnitude and the stress magnitudes.
Stress that will also
In,
not change. Hmm.
so instead of 200 gigapascal, it may be break something else due to I increase the area.
Uh, no, no, strength will always remain same. Strength will not vary depending upon the cross section.
Okay, sir.
Yeah, strength will always remain same. So you won't see depending upon the load. Yeah, strength will always remain same. Only at that stress, because that's why we say strength. Only at that uh, strength is always constant. Only at that stress, material will fail.
No, no, yes, sir. I talk about only stress, not about strength. Stress may change, na, sir.
Yeah,
Huh.
stress may change, but stress when stress reaches like some point, like this point, upper yield point, or let's say this point, these are limits. At this stress, the material has to yield, and at this stress, the material has to what you say, go to strain softening. At this stress, material has to fail, like that. I'm saying.
Understand, sir.
Yeah. I'll also check it once. So the standards whichever we use are basically to make sure that people don't uh, make the results inconsistent. So if all the people are using same standards, it will be easier uh, to follow, and everything gets standardized. Yeah. It this strength will remain same, but if you take like some observed very huge cross section, like instead of taking a small bar, you take a big block. So then the thing is, there may be some disturbances, you cannot apply the load uh, such that stress is uniform across the cross section. So then the may get disturbed. So if you have a small rod, you can make sure that the stress is at the end points when we apply the load, the stress will be not uniform across the cross section, because you might have seen professor explaining the Saint Venant's law. That's why we go away from the holding joints and we take the gauge length, and in that only we measure it. So that's why we make a dog bone sample. So as long as the cross section is like not uh, cross section dimension is not varied abruptly, like you take a big block and do a tensile test, uh, as long it remains very thin, like I hope you can understand. Like if it remains same, then you can make sure that the cross section has stresses same. So then the strength will be same. If we
Yes, sir,
take
sir.
some observed cross section, some other things may come, like load may be not applied properly, or sometimes movement may come. Then your strength may decrease. But that's why there are standards to take the specimen like this much. Uh, ASTM standards, like, and also Indian standard code. Like if we go into, I am a civil engineer. Like if we go, uh, we take I think a half a meter or some rod, mild steel rod, and we place it in the universal testing. So in mechanical engineering, ASTM standards are different, but we have to make sure that we follow them. Actually, according to the industry standards, may differ. Specimen
Understand,
standards.
sir. Sir,
You are
another
from
question is,
mechanical, yeah,
sir, in the according to the standard, the specimen cross section is circular.
yeah,
So my question is that is it matter if so suppose sir if a 50 diameter or suppose 10 diameter,
mm,
whatever the area I can take a elliptical cross section and I can take the same area of a square cross section. So my
mm,
question is that is it affect the graph in the point of necking? Because sir
ah,
my question is that
mm,
sir we
mm,
are generally consider that this graph as a
mm,
maximum yield point or whatever, but in
mm,
our general engineering practice we have so much things, so the square bar
mm,
is there and various type of bar is there, but for our
mm,
convenient we only use this bar, means this
yeah,
graph.
yeah, yeah, yeah.
So sir,
Uh,
my question is that the cross section area may vary, means it may change the something, sorry.
Shape of the cross section may sometimes change it, but there are also ASTM also gives standard which has a rectangular cross section. Rectangular cross section is also there, but generally it is preferred that whatever we are generally we take rounded bars, because uh, or a circular cross section bar, because there is no concentration of stress at endpoints. When you take a circular bar or different things, there might be some changes like here and there. Stress strain, uh, but there will not be a very huge change in this graph. Like this will remain like this only. You have a elastic limit, then you have a yield point, then you have a strain hardening, then you have a strain softening. Like that.
Understand, sir.
Yeah. Rounded bars are used because they have some uh, advantages also. Like as I said, like there is no very huge concentration at endpoints, corners, or something. So things are taken into consideration while designing various, like for construction we take lot of rounded bars. You are mechanical engineering, right? You are from mechanical engineering.
Yes sir, I am mechanical engineer.
Yeah, yeah. So there are like specimens, ASTM specimens for rectangular cross section. Also, there is also a specimen standard for uh, square cross section. Sorry, circular cross section also. So depending upon what we take, but this graph will remain same. So strength of the material is independent of these things. Strength will be same. Yeah.
Understand,
As
sir.
long as you don't take some observed sections, due to that some moment comes into the picture or stress concentration comes into the picture, then test results may get affected.
Yes sir.
So if we conduct a tension test and uh, on an isotropic material, and strain at a point uh, is measured using the strain gauges. So we have a specimen like this, and in this direction the strain gauge is applied, and it is measuring. Let's say this is x y like this, and it is measuring epsilon y phi along strain along the y axis. So we have to, from this we have to find out what is the strain in xx and what is the strain in zz. So the load is being applied in y direction, so there is only stress in the y direction. So sigma y is the only stress here. So when we have the relationship between stress and strain and stress, or stress and strain, whatever you say, epsilon yy is equals to sigma yy by epsilon minus mu into, we also have these things due to the, whenever there is tension applied, the material contracts in the length and breadth directions, breadth and width directions. Due to that, uh, there are different strains occurring, but here zz is also there. Yeah. Here, as I said, only the stress is being applied in the yy direction, so these two things will become zero. Sigma xx and sigma zz will be zero, and this is the uh, longitudinal strain in y direction. If I want to measure the strain in x direction, I'll write the same thing using the Hooke's law. So this is called, also called as Hooke's law, generalized Hooke's law, minus mu into yy by plus yy plus zz by e. So here, as I have said, xx is 0 and sigma zz is 0. That's why I'll get sigma minus mu into sigma yy by e. And similarly, epsilon zz, strain in the longitudinal direction, sigma zz by e minus mu into yy plus xx by e. So only y again. So minus mu into sigma yy by e. So there are lateral strains in xx and yy directions, which are being induced due to the load applied in yy direction. So whenever there is stress strain relationship uh, asked anywhere, you have to give this generalized Hooke's law for an isotropic material. This is the generalized Hooke's law. You have to write this. You should not say stress is equals to strain into Young's modulus. That is only in the case of this, whenever the tensile test is being conducted. Given that tension test is conducted, then you can say sigma yy is equals to e into epsilon yy. But whenever generally if someone asks you stress strain relationship, you have to give this generalized stuff. So then you have to deduce from it, if this is tension test, other stress components are 0. That's why sigma yy by e, and that's how we get it. So we have to make sure that these things are taken care of while these questions, like people can puzzle you over this things. This is how you get the longitudinal strain and the lateral strains for a tension test. And if I have a material, particular material whose modulus of rigidity is equals to the bulk modulus. So he's saying that the modulus of rigidity is equals to the bulk modulus. Shear modulus is also called as bulk modulus. Sorry, shear modulus is also called as modulus of rigidity is equals to the bulk modulus. Then the Poisson's ratio will be. So we have these relationships. E is equals to 9 kg by what is that? G plus 3K. So he's saying G is equals to K. I'll get 9G square by 4G. I'll get E is equals to 9 by 4G. And we also have this relation where E is equals to 2G into 1 plus M. So in this, from this and this 9 by 4, you comparing these two equations, 9 by 4 is equals to 2 into 1 plus M. So if I do this, I will get 9 by 8, 1 plus mu. Mu is equals to 9 by 8 minus 1. So it is 1 by 8. So 1 by 8 is 0.11, I guess. 0.125. This is the Young's modulus when the shear modulus is equals to the modulus of rigidity. Yeah. So these are basically things which are yeah, Devashish, you can ask me a question.
Sir, on which case does shear modulus is equivalent to the the volume at K? What is the scenario?
This material, I don't know what kind of material it will be because Young's modulus is not for metals. Young's modulus is basically not Young's modulus. Poisson's ratio is basically 0.3. I don't know what material is it, but uh, imagine that there is some material for which G is equals to K. So I haven't for if you have, let's say, rubber, then Young's modulus is nearly 0.5. Not Young's modulus. Poisson's ratio is 0.5. But for metals, aluminium, steel, and all, it is nearly 0.3. I don't think there is any metal whose Poisson's ratio is 0.4. But given the question, just assume that there is some material for uh, these things are there. These things are just testing your aptitude, like how you, if this is the case, how you are getting the Young's modulus. Just they want to test your aptitude, like you know the relationship between E, K, and G. So if you substitute, you get E something. From that, if you know a relationship between E and G, you can compare these two things and you get the Young's modulus. So these are just playing with your uh, what you say knowledge, so that they can test your aptitude. Cause so these kind of questions can be asked in GATE. So GATE is basically, as you know, there the name itself says that it's a graduate aptitude test in engineering. So competitive exams have these questions like although it doesn't make any sense sometimes. That me, I don't think there is any material which has v is equals to k. But these questions are asked like how you are using the information or knowledge you have to get some solution. So
Clear, sir.
yeah. Next we will see. So you also have to remember this. This was also explained in the class, like how uh, this uh, the relationship between stress and strain. Sigma ij is equals to uh, this is epsilon I j k l, and this is kl. So this is a fourth order tensor. So fourth order tensor means you can't like basically comprehend this in space also. So second order tensor means you can write a matrix. Third order tensor means you can write a matrix in 3 dimensions like this. You can write something like this. So let's say one three elements, and in another also three elements. So you can imagine it like a Rubik's cube. So it has three nine 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 9 into 3. There are 27 elements in this third order tensor. Similarly, you can't imagine this in space. Fourth order tensor is 3 into 3 into 3 and into another 3. So this is basically a 12 fourth order tensor. So the relationship which gives so this uh, what you say constitutive relationship uh, epsilon ijkl. So is a fourth order tensor, which means it has 3 into 3 9, 9 into 3 27, 27 into 3, which is 81. So there are 81 elements in this fourth order tensor. So from these 81 elements, if we do, if you watch the lecture, like basically there are 81 elastic constants. Then if you do certain reductions, there is like energy relation and there is symmetry of cross shears. If you do certain things, it will come down to 21. So that that is called as for if we have 21 elastic constants, that is an anisotropic material. Anisotropic material. So in order like we know that stress is a second order tensor, like we like write it like this: sigma x, sigma xx, sigma yy, sigma zz, and sigma xy, sigma yz, and uh, sigma xz and sigma yz. This is symmetric. Due to the symmetry, I'll just, for my convenience, I'll write this as a vector of 9 different components: sigma zz, sigma xy, sigma xz, and sigma yz. And similarly, strain also I can write like this, like a vector. It is not a vector, but I am just writing so that I cannot comprehend this. Fourth, I cannot comprehend this in space. That's why I'm writing this like this: epsilon xx, epsilon yy, epsilon zz, xy, yz, xz. And then if I have this vector, sigma vector, and using this, I can write this fourth order tensor in the form of a matrix. This you can see in the lecture. This is epsilon, and this is in order to write this, I'm just this is a for only for a representational purpose. So so we have the Hooke's law, right? epsilon xx, epsilon yy, epsilon zz, sigma xx by e minus mu into sigma yy plus sigma zz by e. So from this, three, there are basically gamma xy is there. Gamma is tau xy by g. So there are, you have 9 equations. So 9 equations, you can decompose it like this, and you can write it like this. So first one, I'll just write first one, epsilon sx, which is mu into mu by e, and the remaining 3 are 0, and you can write like this. This is for isotropic material, okay? So if you multiply this with this, you will get this relationship. If you multiply with this, you get this relationship. This one. So for this also you have something like this. And for gamma xy, you will have something like this, 1 by g. So here in this whole tensor which you have, you can see that there are 3 elastic constants per, but g can be derived from using, if you know mu and epsilon, mu and e. So that's why this is a strain and stress relationship for a isotropic material. In this whole elastic tensor, which we only have 2 independent elastic constants, E and mu. E and mu or E and G. So, or mu and G. 2 are independent. Using that using uh, other things, we can uh, using 2 we can get the other one. But if you go to an anisotropic material, you will have X, Y, Y, Z, and different things, and this also will be populated. So this will not be zero. For an isotropic material, if you apply tensile stress, there will be only tensile strains developing. But if there is an anisotropic material, if you apply tensile stress, shear strain is also developed. So this will not be zero. So all these things will not be zero. So we have this we have this relationship. Then you will get 21 elastic constants for an anisotropic material. This derivation is given. I am just not. I am just giving a brief explanation. You can refer to the lecture for more detailed case. So for an anisotropic material. For orthotropic material means in perpendicular directions, the elastic constants are different. In x direction, epsilon is xx. Young's modulus is some. Uh, let's say if you have wood. Wood is a material in which you can see fibers. So fibers are in some direction. So if you apply stress in this direction, it will be different. Young's modulus will be different in this direction compared to this direction. So if you take any wood, I'm like a stick or something wood, you can if you apply stress perpendicular to the fiber direction, you can easily make it separated, or material fails because the Young's modulus in the perpendicular direction of fibers is less, but here along the fiber direction it is more. So that this is called as an orthotropic material. Okay, in perpendicular directions, the elastic constants are different. So for a 3D orthotropic material, there will be 9 elastic constants. So we have x, y, y, z, epsilon xx, epsilon yy. Sorry, I'm not saying that. Exx, Young's modulus in yy direction, Young's modulus in zz direction, and you have mm, uh, uh, Poisson's ratio in xy, xx, xy, yz, zx, Poisson's ratio, and you have different this also. So xy, yz, and zx. So here these are not independent, like these are not dependent. That relationships which we give, those were for isotropic. For orthotropic, this will be different. So that is not the scope of this course. You just remember that there are 9 elastic constants. So when you go for a 2D orthotropic material, 2D orthotropic, case, you have xx, yy, xy, and xy. So there are only 4. So in z direction, everything is 0. Yeah, Devashish, 4 elastic
Sir,
constants.
in
Yeah,
sir, in orthotropic, they not follow the this equation. The E is equal to 9 kg by G plus 3 k. This relation they are
no,
not
no, no,
following.
no, no, no. That is derived for an isotropic case. That
Understand,
is
sir.
only for isotropic. All the relationships which I gave are only for isotropic case.
Okay, sir. And sir, E is the four-dimensional. Sorry, so that is the fourth order tensor. E, the Young's modulus.
Yeah, Young's modulus is the fourth order tensor.
Clear, sir.
Yeah, fourth order, as I said, third order is you can imagine it like a cube. This thing is like you can like you don't take much effort on this. Just remember like how many elastic constants are there for which, and just get a brief understanding how these constants are being get. Uh, but when you go to higher studies, like if you do a master's or PG course in advanced solid mechanics, there you can learn it more deeply, like how this thing is being developed. But this course is basically we are dealing with 2D things and mainly on isotropic materials. Okay, so 9 4. Okay, and isotropic, as I said, isotropic has 2 elastic constants, 2 independent elastic constants. The next, okay, we'll see something on temperature now. So, say a steel rod is given, and Young's modulus of steel is given as 220 gigapascal. Hmm. And coefficient of thermal expansion. This you might have also learnt in your engineering mechanics course. Coefficient of thermal expansion. And the steel rod is of 2 meters uh, length, 2 meters long. It is at a temperature, initially it is at a temperature of 30 degrees Celsius, and then it is increased to 100 degrees Celsius. The temperature is increased to 100 degrees Celsius. If the expansion is prevented, we have to find out what is the stress. So the thing is, whenever there is increase, let's say if you have any, it's a rod is like this. Whenever there is a temperature increase, all the materials are basically all materials like metals basically. I don't want to talk about other materials. Metals basically expand whenever there is increase in temperature. They will expand. Expansion is such that it their dimensions increase in all the directions, not just in xy, not just in xxyz. So metals will expand. So due to this expansion, strain is being developed. That is called as thermal strain. So, but the thing is, there will be no strain, there will be no stress. So, because it is freely expanding due to the thermal property or coefficient of thermal expansion it has. It freely expands without any stress. Whenever you increase, it will expand. But there will be strain due to the increase in temperature, but there will be no stress. But what happens that I have a rod like this. Instead of keeping it free at this end, I fix this end also. Now, when you increase the temperature from 30 to 100 degrees Celsius, the metal wants to expand. This rod wants to expand, but it is restricted by this boundary. So, this boundary is making its natural property of material to expand to a temperature increase is being restricted here. So, whenever there is some restriction, whenever there is some opposition, you develop, the materials will develop stress. So inherent property is to expand. It wants to expand due to that increase in temperature. But as the increase in temperature is encountered with a boundary here, that the free end is also fixed, so it cannot expand. So uh, that's why. So this boundary uh, uh, will give off stress on the rod. Did you understand this?
Yes, sir, I understand.
Yeah, then it's fine. So we have this uh, we have this coefficient of thermal expansion. So coefficient of thermal expansion is basically uh, per strain per unit change in temperature. So this is the coefficient of thermal expansion. So if I know this thing, L by L, if I know that coefficient of thermal expansion and the temperature change, I can calculate the strain. So thermal strain. So let's say here I have this given thermal strain is here. Let's say I'll take it as uh, a strain only, epsilon, and this is 1.2 into 10 to the power of 5, 10 to the power of minus 5. And the change in temperature, this is per, you should be, we should be careful that this is given per degree Celsius, and the temperature change also should be taken in degree Celsius only. So this is 100 minus 30. So if I do this, 1.2 into 10 to the power of minus 5, I will get thermal strain as 8.4 into 10 to the power of minus 4. So this is the strain. But uh, let's there is a boundary. So the it is restricted. The rod is restricted and it is not allowed to expand. So assume that the material has expanded due to the temperature change, and now you are trying. Now you will apply some load and bring back to its original dimension, uh, which is reducing this strain. Like it has expanded, and now we apply and it will bring back to its original dimensions. So expansion is reduced due to the boundary. So we know the stress strain relation, that is sigma is equals to E into epsilon. Just because the boundary is only present here, and as I have said, only it take it as a tensile test. That's why I'm taking sigma is equals to E into epsilon. So generalized Hooke's law is not taken directly because the boundary is present in only one direction. So displacement is restricted in one direction. And that's why stress will also be developed in one direction. So I know sigma and I know epsilon. I know E is also given. So 220 gigapascal, 220 into 8.4 into 10 to the power of minus 4. So if I do 220 into 8.4 into 10 to the power of minus 4, I'll get sigma is equals to 0.1848 gigapascal. So this is the stress developed due to restricting the temperature expansion. Yeah, gigapascal. And if I want in megapascal, instead of this, I can write it like this. Yes, same answer. Yeah. Next, we will see. Yeah, exactly. This is how thermal strains works. So when the material, when there is thermal strain, there is no stress induced. Just it will expand. It is its natural property. But when you restrict this strain, there will be stress developed. So this is the main essence of this. Yeah, Devashish.
Sir, sir, you tell that why not you consider the general Hooke's law here, and why you consider this?
Ah, okay. See, let's say this is um, strain is in, let's say, epsilon xx. I have this right, generalized Epsilon. This is the flow. But as you can see, let's say this is I am taking x and this is y, okay, and some perpendicular direction is z. I have the boundary only in x direction. I am only restricting this axial strain, okay. So I'm only restricting the axial strain. That's why there will be some value for this. And in axial direction, there will be some force which is being applied, or there will be some stress which is being applied to the rod. But in other direction, it is free. I am not applying anything. So these two things will become zero, right? So I get sigma xx by E, right? Did you understand this? Then sigma E into sigma.
Yes, sir. Clear, sir.
Yeah. Next, we have in order to study uh, in order to study the effect of alloying, it is decided to determine the mechanical properties of an alloy. So to determine the mechanical properties of an alloy, they are taking a dog bone sample like this. Dog bone sample is taken and conducting the tensile test on that. So like this is dog bone sample is put in the UTM and the tensile test is conducted. And there are two strain gauges attached. One is in the YY direction and the other one is in the XX direction. So let's say if I take this XY, so epsilon XX and epsilon YY can be derived from the strain gauges which are pasted on the specimen. When that is load is applied, strain induced can be taken from the strain gauges, and it is given that this strain is 1500 micro strain. Micro means 1500 into 10 to the power of minus 6, and strain gauge 2. Sorry, this is YY actually, and this is XX. Because the stress is being applied in the YY direction, it will elongate in that direction. In the XX direction, the material will contract. That's why the strain will be negative, which is minus 4 mu epsilon. And they have also given this graph, stress strain curve, stress given in NPA and strain given in microstrain, and this thing is given 500. One point on this is given 500 microstrain, and this is 1.105 megapascal. So from this, first we have to find out the Young's modulus. So what is Young's modulus? Using this graph and the information given, how can you find out the Young's modulus?
The slope we can take the 10 theta.
Yeah, exactly. Slope we can. Won't need to take this. Just we can take the uh, ratio of this. So tan theta is basically stress by strain. So Young's modulus is stress by strain. You know the stress and you know the strain. 105 by 1500. This is given in microstrain. That's why I'm taking this as 10 to the power of minus 6. So if you divide it by this, we will get
Sir, the question
70,000.
is
Yeah.
450 na sir. Sigma xx is equal to 450 epsilon xx.
No, no, no. No, no, no. So that is a strain measured. But you see this graph. At this point, this is the point on the graph, and here it has given. They have given stress is 1500. Sorry, strain is 1500 micro strain, and stress is 105 megapascal, right?
Clear sir. I'm wrongly.
Yeah, yeah, yeah. This information is for other thing. We'll see that. So we got 70,000 megapascal. If you want to take it in gigapascal, 70 gigapascal. So mega is 10 power 6, giga is 10 to the power of 9. So this is the Young's modulus from the stress strain graph which we got. So now we have to, given the strains in perpendicular directions, we have to find out the Poisson's ratio. Poisson's ratio is basically minus of lateral strain divided by longitudinal strain. So here the lateral strain is in x direction and the longitudinal strain is in y direction. So if I take mu is equals to minus is plus 450 by 1500. I'll get mu is equals to 0.3. This is so in general the material for you just remember that for any metal this will be the Poisson's ratio 0.3. For aluminum this is given the material which is given is aluminum alloy. But for all materials the Poisson's ratio is nearly equal to 0.3. Now we have to get the modulus of rigidity. So we know E and we know mu. From that we have to calculate G. So we know the relationship between mu and E and G. That is G is equals to E by 2 into 1 plus mu. So if I just do it 70 by 2 into 1 plus mu, 70 by 2 into 1 plus mu, which is 0.3. I'll get G is equals to 26.923 megapascal. So this is how
Sir,
we take. Yeah.
it will come in GPA na sir. Already 70 GPA you consider here.
Oh, sorry. 70 GPA. Yeah. So now we know E, mu, and G. Now we want to calculate what is the bulk modulus. Bulk modulus, which is K. So K and E can be related like this. K is equals to E by 3 into 1 minus 2. So implies K is equals to 70 by 3 into 1 minus 2 into 0.3. I do this. I'll get 58.33 gigapascal. So this is the bulk modulus. You got it?
Yes, sir. Said clear.
Yeah. So this is how we take the experimental results and we can derive various elastic constants uh, using that. So next we have to find out something. There is something called Lami's constant. Okay. So if you watch the second lecture, you can see this mu e into 1 minus 2 mu 1 plus mu. So this Lami's constant is basically uh, we know that generalized Hooke's law is like this epsilon xx epsilon yy, and you can write it like this in matrix form. So 1 by sorry 1 by e minus mu by e. This is uh, strain to stress. We know the stress, and from that you can calculate the stress strain. But if you go like this, if you take this inverse of this, if I know the strains and I want to calculate the stresses, something called Lami's constants will be useful here. So there are two Lami's constants, lambda and mu. So these are basically nothing but relations uh, like elastic constants are there. As you can see, this is one Lami's constant, which is lambda. This is basically giving relationship between uh, a relationship having E and mu. So just I know the stress from that I know the strain from that I want to take the uh, to give this relationship Lami's constants are used. From Hooke's law we get this like E and mu you can directly get, but if you invert this, so uh, this is just these constants are just made up for the better understanding and for better representation. Lami's constant. So yeah,
Sir, again, please repeat, sir. Why Lami's constant is used for?
see you have elastic constants, right? For isotropic material, we have elastic constants, two independent elastic constants, E and mu. Uh, E and mu. From that, you can find out G. That is clear.
Clear, sir.
Yeah. So this thing you understood. Like we have the stresses, we have the strains. Let's write it again. Sigma epsilon xx is there. Epsilon yy, epsilon zz, gamma xy, gamma xz, gamma yz. So using the Hooke's law, I can write it like a matrix. Relationship between strain and stress. Says sigma or tau. So basically I'm taking all the equations. I'm just writing in the matrix form. If I multiply this and this, you will get the Hooke's law. So you know, right? So E is equals to sigma xx by E, epsilon xx is equal to sigma xx by E minus mu by E into sigma yy minus mu by E into sigma zz. There, because it is an isotropic material, there will be no uh, 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 due to there will be no like due to shear stresses, there will be no longitudinal strains. This you understood?
Yes, sir.
This you know, right? Just I'm writing it as matrix. Hooke's law, I'm writing it as matrix law. If you multiply this, you will get epsilon xx is equals to sigma xx by E minus mu into uh, sigma y plus sigma zz by E. Simple thing. And you have this g 0 0 0 0 0 0 1 by g 0 0 0 0 0 0 1 by g. But here you have stresses, and if you multiply the stresses with this matrix, you will get the strain. This is the Hooke's law. Let's say you know stresses, you know strains, and from that you want to get the stresses. This means you have to invert this matrix. So inverse of this matrix, all these things can be written like this using this Lamis constants. Okay, something like, I'll just write it down. And this is epsilon xx and epsilon yy and epsilon zz. And similarly, this lambda plus 2 mu lambda lambda plus 2 mu 0 0 0 and 0 0, and this is mu 0 0 0, this is mu 0 0 0 0 0. So if you substitute this lambda what I have given here in this, and there is also some uh, value for this, this nu is basically equals to z, and lambda is equals to mu into e by 1 plus 2 1 plus mu minus 1 minus e. So in order to simplify this matrix, like instead of writing this big term substituting here, we are taking this Lamis constants. Okay, you got a sense?
Yes, sir.
Okay, I can write this if I invert this matrix, I will get this mu e into 1 plus mu into 1 minus 2 mu plus g uh, plus 2g. So like a lot of complicated thing, like in this matrix, big things should be written. But instead of writing these big things, I'll take these constants lambda and mu and simplify it, so that matrix looks uh, very consistent and readable. Yeah. Lamis constants are also two for isotropic material. Yeah. So from that question, we know mu was calculated as 0.3 and 70 GPA. Mm. E was 70 GPA, right? Yeah, 70 GPA. Yeah, and 1 plus mu, 1 minus 2 mu. So if you do this, you will get first Lamis constant as lambda is equals to 40.3846 gigapascal. This is the Lamb's constant. Any doubt?
No, sir.
Okay. Now we will see another question on so there is a signboard like this, and it is having some mass which is 500 kgs. Signboard is having some 500 kgs of mass, and it is suspended by rods. Three rods. Two rods are steel rods at the end, and this is having length. These two rods are having length as 0.5 meter. Diameter of this rod is 30 mm, and 200 GPa of Young's modulus for steel, and coefficient of thermal expansion of steel is microstrain per degree Celsius. 11.7 microstrain per degree Celsius per steel. This, the middle rod, is a brass rod. So it has a length of 1 meter. Diameter of brass rod is 30 mm, same, and epsilon B is 83 gigapascals of brass rod, and the thermal expansion coefficient is 18.9 microstrain per degree Celsius. So initially it is at room temperature, and that is like 30 degrees Celsius, and then the temperature is increased to 45 degrees Celsius. And we are going to neglect the self weights of these rods. Now we have to find out what are the effects in this. Let's say if there is uh, if the signboard also has if the signboard also is a massless signboard, like instead of 500, let's say it is 0, then what what of the rods will experience the compressive forces due to the thermal stress. So the thing is, you can see that compared to the steel, brass rod is having thermal expansion, coefficient of thermal expansion on a higher side. It is 18.9 compared to the thermal coefficient of thermal expansion of steel, which is 11.7. So when temperature is increased, brass rod is going to expand more, but the steel bar is going to expand. It is going to expand, but it is going to expand less. So what happens is that because these are all three are connected to a signboard, so the thing is the deformation, the elongation in all the three bars should be same. So due to this thing, what happens is that uh, this will expand, but brass rod will expand more, but steel rods are expanding less. So that's why, but all three should be having same dimension, same expansion. So due to the signboard connected, that's why the steel bars will experience tension, and the brass rod will experience compression. Did you understand this?
Yes, sir, clear. Because uh, the brass rod try to expand more, elongate more, but in the meanwhile the
Yeah,
two steel rod are compress, they try to
steel
compress
rods.
it.
Yeah, they try to compress it because their elongation is less. That's why they try to compress it. So
Yes,
brass rod is experiencing compression, and the steel rod is experiencing the tension here. So so this is not brass, actually bronze. Just read it as bronze. Bronze rod is having compression. So the next thing we have to calculate is what is the stress experienced by the uh, uh, steel rod uh, due to uh, the temperature change. So we have to take here compatibility condition, which is uh, the deflection deflection in steel should be equals to deflection in the bronze. So we know that this is the case, and change in length can be given as we know that change in length can be given as length into alpha delta t. Length of steel. Okay, okay. Just think if I, so as I've said, the mass of this is 500 kgs. So if I want to get the weight, which is W, M is M into G. G is given here as uh, 9.81. So 500 into 9.81. You get 4.905 kilonewton. So this is the weight. This weight, whatever we are giving the weight, should be equal to the uh, the loads which are carried by the three different rods. So weight is equals to first load in the first rod plus, and then the bronze rod, and then the again the steel rod. This should be equal to this, and what do you have? This is basically the initial state, and we have just look.
Again, the thermal effect compressive, megapascal compressive,
Speak again.
Hello.
Yeah, Debashish, yeah.
Sir, my question is that by digital imaging correlation, we cannot tell the magnitude, na sir, because it is only the light fringes only.
What magnitude of what? Strain?
The strain.
Yeah. No. Digital image correlation is for stresses only. Digital image correlation is an experiment conducted for, sorry, digital image correlation is conducted for strain. Okay. So in digital image correlation, we have a sample on which uh, you paint these speckles, black dots. Okay.
Yes,
So
sir.
after that, you take lot of images, and load is applied. While load is applied, lot of images are taken, and after that, you feed that images data to computer and process these images from one time instant to other time instant, like as load is increased. So distance between these dots are there, right? Small dots. Distance between these dots is calculated. So, and also the slopes, gradients are calculated. So how is you wearing, like do you by do y? So displacement gradient is calculated and displacements are calculated, small displacements. From that, you can get the strain. Okay. So digital image correlation is done for getting the strain field. For whole field you can get the strains. So at every point, you can get the strains. Got it?
As
Devashish?
depend
Hmm.
the
Yeah.
selection of strain gauge is depend upon the materials. If you use fiber or if you use metal, then you should go for the different resistances. So I'm confused here
Yeah.
because in the
No,
suppose I
no, no. We are talking about the strain gauge, right? Sorry, we are talking about digital image correlation. So why are you asking about strain gauge here?
hello.
Yeah. Ask.
Uh, so the previous question, whatever now you that clear. Now the second
Hmm.
question is that, sir, this one.
Ah, what is the second question?
The second question that according to material we should select the selection of the different resistances strain gauge we should
Yeah,
select.
yeah. Yeah, we have to resistances, like if you take a composite, and if there are thermal effects, all these things should be taken care. Like strain gauges should be taken accordingly.
Okay, sir, clear.
Yeah, it's clear, right? So here I have got this. ID. I'll just clear this today for today. So we got this relation, okay? In this, we got this relation. You just forget this. So this relation is total deflection due to the thermal strain and total diffraction due to the thermal strain in bronze and total diffraction due to the thermal strain in steel. So in this, the deflection first we can break this into two parts. So due to the coefficient of thermal expansion, some elongation will be there, and due to the tensile stress, some elongation will be there in the steel rod. So it is not for it is not fully being expanded. It is not uh, uh, what uh, it is having some extra steel rod. Steel rod is having thermal expansion initially due to the temperature change, and in addition to that, because the bronze rod is expanding more, so it will expand a little bit higher than the natural elongation. That is due to the thermal stress. Okay, due to the thermal stress. And this bronze rod will expand due to the thermal expansion naturally, but because the steel rods are having less thermal coefficient, the bronze rod will be dragged back by this uh, thermal stress. So they both will come to some point such that total deflection of this should be equals to 0. And in this, this is basically we know Ls alpha delta T, and thermal stress, deflection due to the thermal stress is basically we have we can write it in the form of E into sorry, Ls into thermal strain due to the strain due to the thermal stress, and this can be written as sigma s by E. So this can be written similarly. Bronze can be written like this, alpha delta T, and this is being reduced due to the steel rods, which steel rods are coming a little bit uh, down, and bronze rod is going a little bit up, so that they can maintain equal displacement. And this is also like L, yes, sorry, this is LB, and sigma V. So we have these two relations, equation 1 and equation 2. So if we substitute the values, we'll get two equations, and from that two equations, we can get the value of two stresses. Is this clear, Devashish? Hello.
Hello.
Yeah. Is it making sense?
Yes,
That
sir.
is
It
the
is.
thing.
Sir.
Yeah.
Again, I go. I will check it again. I will go through it. Then, if any doubt, then the next session I will ask, and I do it
Okay. Okay.
myself.
Okay. 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 So remember this. Like you have to take the equilibrium. So compressive force in the bronze rod should be equals to tensile sum of tensile forces. This is the equilibrium, and total deflection due to the thermal stress in steel rod should be equals to the total deflection in bronze rod due to the thermal stress. Using both this, we can get the thermal stresses. Okay.
So he,
Okay,
sir,
we'll
lastly,
yeah,
what the question asked, find out the strain
find
or
out the
what?
thermal stress. Find out the thermal stress in steel and find out the thermal stress in bronze. So we get these equations, right, in form of sigma b and sigma s, and here also you know all this. Here also unknowns are sigma s, thermal stress due to the thermal stress in steel and thermal stress in bronze. Okay, in this
Yes, yes.
equation and in this equation. Uh, are you getting the two equations, right? You can. I've written it crudely here.
Yes, sir.
Yeah. So here also unknowns are in this equation. Also unknowns are thermal stresses sigma b and sigma s, and in this equation also unknowns are sigma b and sigma s. So we have two equations and two unknowns. Those are the thermal stresses in bronze and steel. We can calculate directly. Okay.
Clear, sir.
So I'll just write. Okay. First, the equilibrium condition is the compressive stress in bronze. The compressive force in bronze should be equals to tensile stress in first steel rod and tensile load in the second steel rod. This is one equilibrium equation. This is the equilibrium equation. And the next thing is we have to get total expansion due to the thermal stress in steel is equals to total thermal expansion in bronze. And steel is getting a little bit extra elongation. So initially due to the temperature change, uh, initially due temperature change, it will have some expansion, and because the bronze is expanding more, due to that there some extra elongation will be there. That is due to the thermal stress, you can say. And bronze will also have its natural elongation, but because the steel is having less thermal coefficient, steel will try to drag bronze. So it will say, okay, you steel steel rods will be like, okay, I'll come down a little bit, you come down a little bit up, okay, so that we can get a equal displacement, equal deflection. So bronze will say, I'll come down a little bit up. That's why it is getting compressed. So from the thermal expansion, we have to take out this uh, compression due to the thermal stress. Did you understand this?
Yes, sir. Yes.
Yeah. So this is basically L alpha delta T. Temperature change we know, LS we know, alpha S we know, and this is uh, 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 thermal stress, expansion due to the thermal stress. I can write this in the form of strain, which is Ls into epsilon thermal, and this again I can write it as epsilon thermal can be written as sigma thermal by Es, sigma S thermal by Es. Similarly, here also Lb into epsilon S minus Lb into epsilon B thermal you will get. So strain due to the thermal stress. So V thermal by Es. Okay. This is Lb into alpha. This is naturally due to the temperature increase. It is getting bronze is getting expanded, but because this bronze is connected with the two steel rods, it will try to bring it up. Steel rods are will try steel rods because bronze is getting expanded more. Steel rods will come a little bit down, like this. These three are there. Three, three are there. Uh, sorry, like this. Three are there. It will expand more, and it will expand a little bit less. But because these three are connected to a signboard, so steel rods are like, okay, I'll expand a little bit for you. You come up a little bit up for me, and after doing it, we'll all get at the same position so that the signboard is remaining in a horizontal position. Did you understand this? This is the extra expansion. This is the thermal. This is normally steel is having the thermal expansion, and this is the extra expansion due to the thermal stress. Here, this is the total thermal expansion of the bronze rod, but it is going a little bit up due to the thermal stress, like this. Now you got a sense?
Yes, sir.
Okay. Any doubt? No, right? Do you have any doubt, Devashish?
No, sir. No doubt, sir. I do it myself. In the next
Okay.
session, I will ask you.
Okay, Devashish. Yeah. Chalo.
Sir, the one doubt is that, sir, the can I
Hmm.
get the chance of intern
Internship.
summer internship? Yes, sir.
So the when is your vacation from? Like when your semester will get completed? Oh, I
I will
can't
free,
hear
sir.
you. Hmm?
Sir, June 10 onward, I will free, sir.
June 10th.
Huh.
So it's like still a long time to go. I'll ask, but they will not say anything because uh, it depends on the work at that time. Like right now, we don't have any projects. Okay, uh, but like I'll give you my contact details and everything. Uh, just before like in May, maybe probably in May, uh, I'll ask once. Now, if I ask, they'll say like, oh, we can see afterwards, like because it depends on the work at that time.
Sure, sir, sure.
Yeah.
So problem is that because though I am the second year student, so
Hmm. Yeah. No, the thing is, you can get like if the faculty is interested, they can take you. Like it doesn't. Like second year student means it doesn't make any difference. If they want to take it, they can take you. But yeah, like instead, like the application which you fill in, right? Summer internship program, I guess.
yes, sir.
That will not. That is one route. But if you can contact, like you are contacting me, faculty is also can take you under consideration. So that is not an issue. So you can
Uh,
get a internship. So that's not a problem. I'll talk like I'll see like now if I ask they will say like we can see afterwards. So
no problem, sir. I wait if it is possible or okay. Otherwise, okay, I'll see otherwise.
yeah. You try other options too. Uh,
Okay, sir. Problem is that
yeah. What?